Okay, so in question 6, we are looking at which species can make the most ionic bond. So obviously you're looking for a species that can make a positive charge easily, and a species that can make a negative charge easily. So we are comparing magnesium and potassium for the positive charge. Well, we know that magnesium has a smaller ionic radius compared to potassium and a smaller atomic radius compared to potassium. And therefore, it is more difficult for the magnesium to lose its outer electron, and also it needs to lose 2 outer electrons, so it has 2 ionization energies that it has to go through, whereas potassium only has 1 outer electron and it only has 1 ionization energy. And that first ionization energy of potassium is lower than the first ionization energy of magnesium because there's more shielding in potassium. So therefore it's easier for the potassium to form a positive ion than it is the magnesium. For the negative ion, we're comparing sulfur and chlorine. So again, chlorine has a smaller atomic radius than sulfur. So therefore, it's easier for chlorine to attract the 1 electron that's needed to make the ion than it is for sulfur to attract the 2 electrons needed to make the ion. Therefore, it takes less energy. In fact, energy is released when chlorine gains an electron compared to the endothermic process of the second electron being added to an already mono-negative sulfide ion. So therefore, chloride forms the ion more readily than sulfide forms its 2- ion, and therefore it makes a more stable ionic compound because the process is exothermic overall. In question 7, most of you answered this question quite well. We're looking at a 6-mark question comparing the bonding in boron trichloride with nitrogen trichloride. So boron trichloride has 3 electron environments. All of them are bonding pairs. So therefore there's no lone pairs. So therefore there's no lone pair repulsion. And it takes the ideal angle of 120 degrees. Where did we get that 120 degrees from? Well, it's 2-dimensional. So the maximum angle a 2-dimensional shape can have is 360. There's 3 bits to that because there's 3 electron pairs. 360 divided by 3 gives you your 120, and it's trigonal planar. In the NCl3, now we've got 4 electron environments, 3 of them being bonding pairs and 1 of them being a lone pair. The lone pair bonding pair repulsion is greater than bonding pair repulsion. The ideal shape, if there was no lone pairs, would be tetrahedral, but a lone pair reduces the bond angle to minimize repulsion and maximize separation. So you get an angle of 107 degrees with a trigonal bipyramidal shape, where the lone pair takes up one of the spaces of the tetrahedron. In the second part of that, you are asked to draw a dot cross diagram for boron chloride and explain why it's electron deficient. Boron's in group 3, therefore it has 3 outer electrons, so you had to have 3 crosses or 3 circles for your 3 boron electrons. There are 3 boron chlorine bonds, so you had to have 3 lots of 2 electrons in 3 distinct overlaps. And the electrons had to be of different coding, 1 cross the other dot, 1 cross the other dot. The chlorine has to have 8 electrons in its outer shell, and you have to have 7 of the same coding, because chlorine as an atom has 7 electrons in its outer shell. So here I've got 7 dots, 7 dots, 7 dots. The reason why it's electron deficient is because borane's only got 1, 2, 3, 4, 5, 6 electrons in its outer shell, and an outer shell to be stable normally we would say would have 8. We call that the octet rule. So because 6 is less than 8, it's therefore electron deficient.